Hi, time for more related rates. Yay! Woo, woo. It helps if you cheer for something. This is what we get to do today. Let's go. Okay, a cone has a diameter of 10 inches. That's nice. And a height of 15 inches. So the entire cone has a diameter of 10 inches, height of 15 inches. Water is being poured into the cone. So I'm going to draw this actually. So here. And water is being poured into the cone so that the height of the water level, so inside there's water, and it's changing a rate. So the water's coming from here somewhere. I don't know who's pouring it in. This isn't real water. Again, this was just me drawing a picture. And this water is being poured into the cone so that the height of the water level is changing a rate of 1.2 inches per second. Okay, so much important information. At the instance when the radius of the exposed surface area of the water. This is kind of crazy, but think about this being like an open cone, like if you were looking into a traffic cone or something, and the exposed surface area. So this one is just a circle. So if you're looking at the top of this cone, it would just be a circle. This is a circle. Of the water is 2 inches. So this is saying in a moment. At what rate is the volume of the water changing? Oh man, so much stuff. Okay, so starting at the end, the volume of the water changing. dV dt is the thing that I'm trying to find. A cone has a diameter of 10 inches and a height of 15 inches. You might think right away, well, this is constant. But what's going to be kind of tricky in this is that if I have a cone, there is actually going to be two different cones that I'm talking about. There's going to be a cone on the inside here of the water level, and there's going to be a cone on here where this is the entire height up there. So we've got a big cone and then we've got a smaller cone. It says the cone has a diameter of 10 inches. So this big cone, I know it's not changing, so I'm going to say the radius is 5 inches. So I know that right now, and I'm not going to write it in these blocks, and you'll see why in a second. Water is being, but I can say radius is somewhere in the problem. Water is being poured into the cone so that the height of the water level is changing at a rate of 1.2 inches per second. So height I know is in here somewhere. And I know dH dt is equal to 1.2 inches per second. Okay, what's tricky about this is we just said this whole height was 15 inches, right? We didn't actually write it in the chart, but 15 inches. 15 inches is this entire thing. I'm going to get another marker. What we actually have is the height of the water. So if this is my water, the height of that water, this is kind of hard to see, would only be from here to here, whatever the top is to the bottom. So this is my height of the bottom. This is my radius, but of the water level. So it's like we've got two cones going on at the same time. They both have the radius and the height, and I've got a volume of some sort. But notice down here, it doesn't say anything about dr dt, and that's going to be kind of tricky. If I'm talking about anything remaining the same on the inside, this radius is not going to stay the same, this height is not going to stay the same, but these two things, the 5 and the 15 are. This one is like, get ready, because it's probably the most complicated kind that we can do, but if you get this one, you are set for the others. So what's going to happen is that none of these, like this 5 and the 15 are constant, but the R and the H are not. But do you see how there are two triangles here? There's that big one that's 5 and 15. And then I've got a smaller triangle in here. And this is a right angle and this is a right angle. This is R and H. This relationship, whatever this, like as one changes in the other one and how they relate to one another, because these are similar right triangles, this relationship stays constant. Okay, so there are several ways that you can write this, but what I'm going to write is I'm going to say big height over little height, big radius over little radius. You could have done this another way. You could have said big height, big radius, little radius, and done them different ways. But if I cross multiply, regardless of how you did this, you should have gotten 15R is equal to 5H. And then I'm going to leave it here, and I'm just going to say, you know what, that relationship holds regardless of what this figure looks like, and I'm going to come back to this in a second. Okay, and it says down here, write an equation, often a geometric formula, that relates these things. So I've got the V, the R, and the H. So I want something with the volume of a cone. The volume of the cone, if I go back a few days, I think it's on that first page that we did. The volume of a cone, yeah, there it is 1/3 pi r squared h. There's a really cool thing in that you can do with how the volume of a cylinder with the same radius, same height, is 3 times that of a cone, but we're not in geometry, so we won't do this here. This would be given to you. And then it says implicitly differentiate with respect to time. I'm not going to do that yet. And this is where it's really important that you want to start, do something so you can remember this later. But if I took the derivative right now, I would do the product rule, and I would have a dr dt and a dh dt somewhere in the problem, and a dv dt. I can see up here or up here that there's nothing with dr dt given. So I want to get rid of the r's. And so, sounds like I'm like a bad pirate joke or something. Anyway, get rid of the r's. Anyway, so what I want to do is solve this for r. 15. So r is equal to 1/3 h, because this is a constant relationship. Then if I come down here, volume is equal to 1/3 pi. Instead of r, I'm going to write 1/3 h. And then I'm like, okay, this still looks gross, but at least it only has h's. Before I do anything else, because I don't want to do the product rule, I want to simplify this. So sadly, no calculus yet. This would be 1/3 pi. 1/3 squared is 1/9. H squared. And then I've got h. And then I'm going to say one more thing. I'm going to say 1/3 times 1/9 is 1/27 pi. And this would be h cubed. That's a lot of work, but you're going to have so many friends. Okay, this is no calculus so far. I'm just saying this volume. This is the relationship because this was a constant relationship. I can put it in before I take the derivative. Now I'm going to implicitly differentiate both sides. So I'm looking at this one. Now I can say the derivative of v is dv dt equals, on this side, 3 times 1/27. I'll just keep it as 3/27, or you can say 1/9 pi h squared, so I'm taking the exponent down by 1, times, wow, dh dt. If I want to simplify this, just because I know I'm going to have to substitute in a second, I'm going to say 1/9 pi h squared dh dt. Now it says substitute all instantaneous rate of change and the values and solve for the variable, the remaining rate or variable. In this problem, it was asking at what rate is the volume changing? So that's what I want to find. dv dt. 1/9 pi. We said dh dt was 1.2. So I'm going to put in 1.2 here. And you might be asking, well, what is height? Okay. This says when the radius of the exposed surface area, so this radius right here, is 2 inches. I don't have a 2 here. I can't put that here because that's h. But what I do know is that r is equal to 1/3 h. So if I know that in this case the radius is 2, given in the problem, multiply by 3 on both sides, I get 6 is equal to h. Whew, it's a lot of stuff, but I keep going. 6 squared is 36. 36 divided by 9 is 4. 4 times 1.2. What is 4 times 1.2? 4.8. I'm going to leave this pi here just because this is okay to just use one place after the decimal because this is the most exact answer that I could give. dv dt, you have to put the units. And volume in this case, does it say? It says that the height of the water level is changing in inches per second. Volume is like, think about it in a cube as length times width times height. So it'd be inch times inch, or cubic inches. This was per second. This will still be per second. And if you wanted to wrap this up, you could say when the radius, I'm looking at the very edge of the problem, or the end of the problem, is 2 inches of the surface area of the exposed water, because I didn't actually say that, and it seems like there's multiple radius here. Okay, so I'm just rephrasing the question. When the radius is 2 inches, DHDT, or in this one, or this one's volume. So I'm going to say the volume is changing at a rate of 4.8 pi inches cubed per second. Whew, that was a big one. If you got that one, great. If you didn't, it's okay. We're going to practice more with those, but let's keep moving on to another kind. So the next kind, we no longer have the guide, which could be kind of nice. These are all pretty similar. A ladder is 25 feet long, leaning against the wall of the house. So 25 feet long. This ladder is always 25 feet long. In any of these problems, these are cheap ladders. Well, ladders aren't cheap, but these are ones that are like, I don't even know where people would store them because they are stuck together. They cannot change. They are 25 feet exactly. This is a constant. Constant. The base of the ladder is being pulled away from the wall at a rate of 2 feet per second. So if we're talking about a wall, here, look, this is a window. Look, this is my wall. Or you can say my wall. Like, there's a house. Ah. Or if you don't want to do that and you just want to write, this is my wall, you can do that. We've got the base of the house, and I'm hoping that the base is going to be at a 90-degree angle with the house so that, you know, unless the house is leaning, which I'm hoping not. And then the ladder is over here. I realize this is not a scale unless a house is really small, but whatever. This is 25 feet. I can put this in right away. I'm going to put base down here just so we can see. And it's saying the base of the ladder is being pulled away at a rate of 2 feet per second. So this is base. This would be my dB dt. How fast is the top of the ladder moving down the wall? Okay, so we got to be careful about that. That's going to be my dHdt, or if you want to call it dWdt, you can, but I'm calling it h for height. I don't like doing these ones in A and B, like a squared plus b squared is equal to c squared. I don't like doing it that way because I don't really know which one's A and which one's B, since those are interchangeable. Base and height, I do. So in this problem, I kind of gave this way, but what relates this would be the Pythagorean theorem. 3 sides of a triangle, a squared plus b squared is equal to c squared. Differentiate after you put in the constants. So there's a constant of 25 feet. Instead of A and B, I also want to change this because I just said that's kind of lame when we put it in that. So I want to change this to B and H. I guess I could have cut B the same, but you know, B and H. B squared plus h squared is equal to 25 squared. Okay, the next thing, now I can differentiate. This would be 2b dB dt plus 2h dH dt equals, what's the derivative of 25 squared? 0. If you said 25 squared, it's not. Or if you did 2 times 25 or something crazy. Derivative of any constant is 0. If you don't do this part, the rest of it's going to be messed up. The next thing, so I'm just substituting in what I know. So I know this says 2b, 2h. Oh no, I need to know those in some way. Well, there is a moment when the base of the ladder is 7 feet from the wall. It's only a moment. That's why I couldn't put it in first. But this is 7 feet at a moment. This is 25. What I can do is figure out, well, h squared plus 7 squared equal 25 squared. And then I can take 25 squared. Oops, that's not it. I can do this. 25 squared, which I think is 625 anyway. Hey, it is. Minus 7 squared. And I get 576. So h squared is equal to 576. Take the square root of both sides. And you can see right now if it turns out to be something nice, but I don't think this one does. Oh wait, yeah, it does. 24. I mean, I totally knew that. I was just making sure you did. Which means now I can substitute this in. The base was 7. dB dt is, we already said this one. It's being pulled away at a rate of 2 feet per second, so I can put that in here. H we just found to be 24. dHdt, that's what I'm looking for because it's how fast is it moving down the wall, but it's talking about the height of the wall. So dHdt is what I'm looking for. And then I want to multiply and actually solve this. So 2 times 7 times 2, what is that, 28? But just to be sure, 28 plus 2 times 24 is 48. DHDT equal to 0. Subtract on 28 on both sides, so I get 48 DHDT is equal to negative 28. Divide both sides. And you could leave it like that and not simplify at all. Or you could say, well, negative 28 over negative 48, or I'm sorry, positive 48, negative 0.583333333333. And I'm doing this because if I use it later, I need the exact answer. Or I could have just said, you know what, I want to do, and I want to leave this as a fraction just in case I need to use this later. This is negative 7 over 12. And this would be feet per second. Yeah, feet per second. We're talking about the wall. But this question says, how fast is the top of the ladder moving down the wall? It is not moving down the wall at a rate of negative 7 over 12 feet per second. So you have to be careful with the language. I'm going to say the ladder is moving down the wall. And here's where I'm going to change it to positive. I'm going to keep my answer DHDT as negative. That's okay. But I'm going to do one like qualifying statement. At a rate of 7 over 12 feet per second. Ta-da! We did it. Okay, next one. Consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing. So this time is area, but it still says 7 feet from the wall. So I still can use any piece of information that I used up here. I can use it down here. So I'm going to say area of any triangle is 1/2 base times height. There's some easier formulas if you've got an equilateral triangle, but whatever. Area is equal to 1/2 base times height. So what I want to do is I want to say, well, now I can take the derivative. So I'm going to say dA dt is equal to, over here, 1/2 b is my first term, h is the second one, product rule. So first times the derivative of the second plus the second times the derivative of the first. The derivative of 1/2 b would be 1/2. And then this would be dB dt. And now I'm going to substitute what I know, because this is all 7 feet from the wall. So everything up here was fair game. So dA dt is the thing that I'm trying to find. And if you want to write that out in the beginning, just so you can be like, what am I trying to find? You can. This would be 1/2. We said the base, when this is 7 feet from the wall, was still 7. DHDT was what I found up here. This is where you can put in the negative, so negative 7 over 12. And if you would have used a decimal, even though this answer would only be required to 3 decimal places, you would have to use all of it, and like as far as you can possibly get in order to have the most correct answer here. So 1/2 7 times negative 7 over 12, plus the height we said was 24, because we did it right over here. 1/2 dB dt. So dB dt was given in the original problem at 2 feet per second. And then it's just putting all these things together. So 1/2. I've actually done all these things before, so I'm going to pretend that I'm doing something. And then in here we get, this would be negative 49 over 24 is the first one, plus 24. And this one I'm actually going to say, you know what, that's approximately 21.958. We're talking about area. The original one was given, this is talking about feet in this problem, and then we have seconds in here. Area is always feet squared. And find the rate at which the area of the triangle is changing. So I'm going to say the area of the triangle is changing at a rate of 21.958 feet squared per second. And I also kind of cheated because I knew I wasn't going to have to use dA dt in the bottom one, so I could do that. Okay, next one's really annoying because you see how this says at a moment 9 feet from the wall? That means anything I did here and here I can't use. I have to just go back to that original problem. So be careful, if it's not at the same instant, you have to recalculate things. Maybe. This one says find the rate, so I'm going to do the same thing as before, just so I know where everything is. 25 is still constant. This is still my base. This is still my height. Find the rate at which the angle, oh man, an angle formed by the ladder and the wall. So this is the ladder, and the wall of the house would be this angle up here. I called it theta. You can call it x or something else if you want. It's changing when the base of the ladder is 9 feet from the wall. Okay, so actually, you know what? I'm going to change it to x. Make this even better. So this is just x. So I need something that relates these other parts. And I need to say, okay, in the original problem, I had 25 feet was a constant. And then I also know the base. So dB dt was 2 feet per second. So I know dB dt is 2 feet per second. And I'm hoping that can help me in a second. I need some equation that's going to relate this angle and something with the sides of the triangle. So, SOHCAHTOA. I can either say sine of x is equal to opposite over hypotenuse, so b over 25. I could say cosine of x is equal to adjacent over hypotenuse, so h over 25. Or I could say tangent of x is equal to opposite over adjacent, so b over h. I want to make sure I didn't mess something up. I think I did. Sine is b over 25. Ooh, this is what it is. Cosine adjacent over, no, we're still good. Adjacent over hypotenuse. We've got this. Okay, all three of these could be correct, but I'm going to tell you 2 are much harder than the other one. The only piece of information that I have is that this, the constant was 25, which I already put in, and that dB dt is 2 feet per second. I don't know anything else because I can't use anything from these parts A or B because this is 9 feet from the wall. So if I did the derivative, this would be cosine of x times, wow, dx dt is equal to, instead of b over 25, think about this as 1/25 b. So I could do this, and it has a dB dt in it. If I try to do this one, I would get negative sine of x dx dt, 1/25 h dh dt. And so I'd have to go through all that work we did from part A and find h. So I don't want to do that here. Tangent, I would need a dB dt, like I would have to do the quotient rule, which would be kind of gross to begin with. And then I would also have to do something with secant squared over here, which would be a little bit harder. And I would have to find dB dt and dh dt. Ain't nobody got time for that. So let's do this one. The derivative of sine was cosine of x. This is where people get, like, later, because this has been on tests in years past and probably something you're going to see in the future again. Really, this whole page, good stuff to know. But people get stuck right here, and they're like, what do I do? Sine, cosine, and tangent are all just ratios. And I can say at a moment when I'm 9 feet from the wall, I know a lot of those ratios. So if this is x, I know this is 25. 9 feet from the wall, I can find 9 squared plus h squared is equal to 25 squared. 25 squared, remember, was 625, but I'll do it again. 25 squared minus 9 squared, which is 81, but I'll just put a 9 squared. I get 544. So h squared is 544. Square root of 544 is 23.2380757. I don't want to rate that every time, so I'm just going to say square root of 544 and leave it like that. Cosine is just a ratio. So cosine is adjacent over hypotenuse. So instead of cosine of x, you know how I said it was h over 25 up here? Instead of writing cosine of x, I'm going to write h, which I now know is square root of 544 over my hypotenuse, which was 25. And then leave it like that. dx dt. Because that's, I think I'm trying to find that, right? Yeah. The rate at which the angle is changing. This could have been d theta dt if we would have called it that, but this is what I'm trying to find. 1/25 dB dt, we know is 2. I'm going to rewrite this a little bit, so I'm going to go up here. Square root of 544 over 25 dx dt. If I would have written this slightly different, it would have been a little bit easier to see. So 2/25. There. I'm going to multiply both sides by 25 over the square root of 544. Because then that would get rid of it over here. If I do it on one side, I have to do the other. So I'm going to multiply by 25 over the square root of 544. Hey, the 25 go away. Dx dt is equal to 2 over square root of 544. And it says find the rate at which the, and I can write this down if I wanted to, but I want to keep going. The rate at which the angle is changing is 2 over square root of 544. And if you want to find what the exact answer is in this one, it's like let's check, 2 over square root of 544. I get 0.085. Or you could say 0.086. You don't have to do either one, and you don't have to do both because you don't want to, you don't want to take the time to do that. I'm just right now. This would be radians because we're talking about calculus. So radians, even though that was not mentioned yet, we've only been dealing with things in radians and calculus. So radians per, the time will remain the same, so seconds. Whew, that was a lot. I know it was a lot, but I'm still going to do one more thing with the last couple minutes. Yes. Well, am I? I'm going to actually make an extra video. I'm going to make an extra video on this one so that it's separated because this is a long time on one. Yeah. Am I? Now I kind of want this all to be in the same video, and I'll just stop it partway through if you need to. Okay, an airplane is flying. I'm sorry, I'm hopefully going to cut that part out because I just freaked you out for a second. Airplane is flying at an altitude of 5 miles and passes directly over a radar antenna. So we've got an airplane. This is going to be such a good drawing. What? That's an airplane. It's flying that way. This is a radar antenna. Boop, 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 boop. Looks like I don't know what it looks like. When the plane is 10 miles past the antenna, so this is only for a moment, like at a moment, 10 miles past the antenna because it keeps flying, the rate at which the distance between the antenna and the plane is changing. So we're talking about the rate up here. So let's call this something. I'm going to call it x. Is 240 miles per hour. So I'm going to call that dx dt is 240. What is the speed of the plane? So in this one, this says the rate at which the distance between the antenna and the plane. I guess I should say this a little bit different. So when the plane, because we're talking about the speed of the plane, this would be the speed of the plane up here. The question isn't super clear though. The distance between the antenna and the plane, meaning the base of the antenna and the plane, is changing. So this would be whatever this would be. Let's call this C. So dc dt is 240. I want to find out what dx dt because that would be the speed of the plane. Okay, let's keep doing this. So I'm going to say, how can I relate these in some way? Well, what's nice about this one is that the altitude, I guess a radar would be down here, which is why it makes more sense because it wouldn't be the whole way up to the plane. That would be a really, really high antenna. Whatever. This is 5 miles. The plane is flying at an altitude of 5 miles the entire time. So the plane's in the air, the antenna is really down on the ground. So I should have said boop, 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 boop. This is sending off a single signal. That'd be weird if it was actually 5 miles in the air too. This base of the antenna to here, this is the C. This is why this is dc dt. I've got dx dt. I need to relate all three at base. How I do so is I'm going to say a squared, or in this case 5 squared, plus x squared equal to c squared. This is a constant, so I can put it in right away. If I take the derivative of any constant, I get 0. So you don't actually have to write that. The derivative of the x squared would be 2x dx dt. The derivative of c squared would be 2c dc dt, because wow. In this problem, if I know this is at a moment, so I'm making a separate triangle, this is 5, and at a moment when this is 10 miles past the antenna, so it flew over top, it's 10 miles past that. What is my C? So I would have 5 squared plus 10 squared. I'm just doing the Pythagorean theorem. I get 125. Just put this here, square root of 125. If you have to write this down, this is okay too. Oh man, I didn't get anything nice. So I'm going to keep this as the square root of 125. I'm going to say this is 2. My x value was up here. So that was 10. My dx dt would be the thing that I'm trying to find. That's the speed. 2c was the square root of 125. dc dt was the one that was given to me as 240. And then I'm going to take both sides and divide this by 20 over here, 20 over here. So dx dt, 2 times square root of 125 times 240 over 20. I'm actually just going to put this in, times 240. I'm going to do that part, divided by 20. Yeah, and so you could do 24 square root of 125, or you could just do times 125 times 24. And I get 268.328. And I have to think about, does this make sense for a plane? Well, it depends on what this is measured in. Miles per hour. Yeah, that makes sense for a plane to be traveling that fast. Okay, and we're going to do 2 more too. I know this is really long, but whatever, stick with me. You got this. I believe in you. Take a stretch break. Ask me questions. Do something. Radius of a sphere is increasing at a rate of 2 inches per minute. So we've got a sphere. Find the rate at which the surface area of the sphere is changing. So you want to go back to, what is the surface area of a sphere? Area is 4 pi r squared. Is there anything that's changing in some way? It says the rate of the surface area of the sphere, the radius is 6 inches, but that's only for a moment. So the sphere is either getting bigger or smaller. Because this is positive, I can see, and increasing, I can see it getting bigger. The radius is changing, the area is changing. So I get, if I take the derivative, dA dt, 2 times 4 is 8 pi r dr dt, because wow. If I take the radius, what do I know? I'm trying to find the rate at which the surface area is changing. So the dA dt is the thing I'm trying to find. 8 pi. This is the radius is 6 inches. dr dt, the rate at which the radius is changing, that's the 2 inches per minute. 8 times 6 is 48, times 2 I believe is 96, but I'm tired so I'm going to check. Yeah, it is 96 pi. And I'm going to say area, because the radius is in inches, the area would be inches squared per minute. Last one, I'm hoping that you took a break. A spherical balloon is expanding at a rate this time. So a spherical balloon, so same thing, but this time we're talking about cubic, which I know has to be dV dt in some way. So because it's the volume. So I want something with the volume of a spherical balloon or a shape. Volume is 4/3 pi r cubed. The volume would not be staying the same whether we get this bigger or smaller, same with the radius. So I'm going to say dV dt, and I can take the derivative right now without substituting any constants in. 3 times 4/3 is 4 pi r squared dr dt. I know 60 pi is my dV dt. 4 pi, the radius is 4. dr dt is what I'm trying to find, and I'm trying to go fast because I know I'm already taking a lot of time. 4 squared is 16, times 4 is 16, or 64. So I'm going to divide both sides by 64 pi. 60 over 64. You can write this, or you can just keep it as a fraction if you want, which is 15 over 16. And remember, this is dr dt, so the rate that r is changing with the rate of time. So in this problem, I'm going to say this would be inches per second is dr dt. And that's at the moment that the balloon is 4 inches. Whew, I kept you for a long time, but I do think you're amazing. Thank you for being awesome. Thank you for learning. This is a lot. We're going to go over more questions like this, so you get a chance to practice too. Okay. Thanks for being awesome.